Hey everyone, today we are going to learn about trigonometric graphs. But before we begin, I want to make a quick request. If you are not already familiar with how basic trigonometric graphs work, for example, how the sine graph looks and behaves, I strongly recommend watching my previous video on trigonometric graphs first. In that video, I explain the foundation of how sine and cosine graphs behave. And if you enjoy visual mathematics videos like this, make sure to subscribe to Hidden Gradient. I upload at least one video every week where we try to understand mathematics through visualization. And if you find this video helpful, please share it with your friends as well. Also, there is something interesting coming later in this video. At the end of the video, there will be a bonus section where I will show you how you can generate and solve trigonometric graph questions using a visualization widget. And the best part is, you can do this without writing a single line of code. So make sure you watch the video until the end. Very often in trigonometry, we encounter expressions that look a little complicated at first. For example, suppose you see an equation like this: y equals 2 sine of 3x plus pi over 4. Naturally, a few questions come to mind. What will the graph of this function look like? Will the wave become taller? Will it repeat faster? Or will it shift to the left or right? The good news is that all of these questions can actually be answered using a simple general equation. Almost every sine graph can be written in the following general form. A controls the amplitude, which means the height of the wave. B controls the period, which determines how fast the wave repeats. C determines the phase shift, meaning the graph moves left or right. And D controls the vertical shift, which moves the graph up or down. To understand these transformations properly, we must first understand the base graph, that is, the original sine function. Y equals sine of x. This curve is known as the sine wave. The graph has some important properties. Its maximum value is 1, its minimum value is -1. So the range of the sine function is from -1 to 1. Another important property is that this graph follows a repeating pattern. The same pattern repeats every 2 pi units. This repeating behavior is called periodicity. Now let's start with amplitude. Look at the coefficient a in the equation, y equals sine of x, and observe how the graph behaves when we change the a. Amplitude controls how tall the wave becomes. For example, if a becomes 2, the equation becomes y equals 2 sine of x. Now the peaks of the wave move higher and the valleys move lower. So instead of oscillating between -1 and 1, the graph now oscillates between -2 and 2. In simple words, A stretches or compresses the wave vertically. Now let's look at B, the period parameter. This controls how quickly the wave repeats. As B increases, the graph compresses horizontally. That means the wave repeats faster. As B decreases, the graph stretches out. So B controls the horizontal behavior of the sine wave. Next comes C, the phase shift. This moves the graph left or right. The shape of the wave stays exactly the same, only its horizontal position changes. If the expression is y equals sine of x minus c, the graph shifts to the right. If the sign were positive, it would shift to the left. Now let's look at D, the vertical shift. This moves the entire graph up or down. The shape stays the same. The amplitude also stays the same. Only the vertical position changes. And this dashed line shows the new midline of the wave. Now let's combine everything into one full example. Y equals 2 sine of 3x minus pi. First, the amplitude changes from 1 to 2. Then B makes the wave repeat faster. Then the phase shift moves the graph horizontally. And together, these changes transform the basic sine wave into the final graph. That is the core idea behind trigonometric graph transformations. Let's do a quick revision. Y equals a sine of bx plus c plus d. A controls the amplitude, B controls the period, C controls the phase shift, D controls the vertical shift. Once you understand these four parameters, you can visually decode almost any sine transformation. Now let's generate the visualizations using ChatGPT. The prompt is in description and you can copy and paste it as it is in your chatbot. The code is getting generated, will take some time. After the script generation is complete, click on the preview button and voila! You can drag the sliders to visualize the graph transformations live. Now here are some real-life scenarios where transformations are used. ECG. Your heartbeat on an ECG monitor is actually a wave pattern. Stronger heartbeat leads to bigger amplitude. Faster heartbeat leads to shorter period. Communication/transmission towers. Every time you send a message or make a call, your phone sends wave signals to transmission towers. Engineers change amplitude, frequency, and phase to carry information. Sound waves. Sound is also a wave. Louder sound means higher amplitude, and higher pitch means higher frequency. Suspension bridges. Even massive suspension bridges can oscillate like waves in strong wind. Engineers use these wave models to keep bridges stable and safe. Music industry. Every song you hear is built from transformed sound waves. Music software literally manipulates amplitude, frequency, and phase to create sound. If you enjoyed this visual explanation, make sure to subscribe to Hidden Gradient and share this video with someone who struggles with trigonometry. I bring new visual math videos every week. See you in the next one.